Today's speaker in the Astrobiology seminar series this quarter is Robert Winglee. He is a graduate of the University of Sydney in Australia, not Nova Scotia. He got his PhD at the University of Sydney in Australia, not Nova Scotia. You may think that this is a bit incestuous and inbred, but this is common in Australia. I got my PhD from the same institution that I got my bachelor's degree. Robert is in Earth and Space Sciences Department. He's currently chair. He's in the Space Physics group within Earth and Space Sciences, and his interests are planetary magnetospheres and also exotic and novel and innovative spacecraft propulsion mechanisms. And he's going to talk to us today about magnetosphere effects in the Saturn-Titan system. Robert.
Thank you, Roger. Yeah, so we're going to talk a little bit about the Saturn-Titan system. And while the photos would typically indicate that these systems are fairly benign and non-coupled, they are in fact coupled due to the plasma there and the magnetic fields that are there in the Saturn system. So I'd like to first talk about what Saturn looks like, and then Titan, and then how they become coupled. So you have Saturn there, gas giant, mainly hydrogen, helium, and a little bit of ammonia, even ice, methane and water ice present there. And there's some question whether it actually has a rocky core or not, but potentially has a rocky core. Very cold. It also has a magnetic field, and that sets up Aurora. So if you actually peek on the bottom side of Saturn, you would actually see that it has Aurora just much similar to our Earth's terrestrial Aurora present. And this arises because of its magnetic field, which then we can sort of, and then when it interacts, well, it's ionized partly by solar UV coming in, also by the precipitation of energetic particles, which then go to making the aurora. So what we have here is not just the planet and its rings, but there's a whole lot of material sitting out here that is invisible to white light. And it is this system that sets up a magnetosphere. And we're interested in these kinds of processes because aurora actually provide remote sensing for the planetary bodies. So this acts like a phosphor screen insofar as it tells us what's actually out here in space, but it also tells us something about what's actually at the planet through the UV emissions. So if you could actually do spectral resolution on those aurora, you'd actually know something about the material up in the upper atmosphere. So it's a means of remote sensing. The magnetosphere itself looks something like this. So here's Saturn again with its rings. It has its magnetic field present, and the magnetic field is aligned with the rotational axis, but the rotational axis is tilted towards the solar wind. So actually the solar wind is coming in, and the Saturn here is a little bit tilted, so actually the bottom side has, in this figure here, a little bit better access to the solar wind than the northern hemisphere. And what happens here is that these are charged particles coming in. They see the influence of the magnetic field, causes it to become compressed on the day side or the side facing the sun, and we have this elongated magnetotail stretching out here. So that's our magnetosphere, and again we talked about the aurora being present. Now little Titan is sitting out here at 20 Saturnian radii, where one Saturnian radii is about 60,000 kilometers, and it sits just about inside the magnetosphere, just at the very edge of this system here. And so Saturn is rotating at about 10.6 hours, so it's sweeping plasma around and into Titan. So there's little Titan sitting there. It's the what we're interested in, it is the second largest moon in the solar system, one of three or depending on how you count it, with thick atmosphere. And that's where the original interest for Titan was that it had a composition that was different from Saturn's, and in fact something that looked presumably like the primeval or the first atmosphere of our Earth. So it has roughly 90% nitrogen pressure, 10% other molecules such as methane. Like I said, this is presumed to be very close to our own atmosphere. The pressure is actually similar to our Earth atmosphere, a little bit larger. It has a rocky interior, silicates present, as well as water ice. The main difference between this system and our Earth is, of course, the temperature, where it's exceptionally cold, and instead of having lakes of water, they actually have here lakes of presumably ethane and methane. So this is one of the latest pictures from the Cassini mission, where these areas here are thought to be lakes of ethane or methane. So they're smooth, different texture, different reflectivity than the other surface material. So that's where it was originally became of interest.
You just point out this is radar images here, not visible image.
Yep. So at Titan, it's a little guy. So even though it's one of the biggest moons, it's 2,600 kilometers radius. So it's actually fairly large. If you put it to our Earth is 6,370 so kilometers. So it's a fair size of the Earth. Its thick atmosphere is subject to ionization, so it has a charge layer around it. It has no intrinsic magnetic field, but the magnetic field from Saturn sweeps by associated with it. So the blue lines here actually I've got this, are magnetic field lines from Saturn. They come in, they see a conductor, they bend around it to produce this comet-like kind of feature, and the plasma flow comes in and around and bends, and you have charged particles gyrating about these magnetic fields. So you have a difference in plasma, you have hydrogen, maybe some light ions like nitrogen or oxygen coming in. You may have a series of different kinds of heavy ions coming out of Titan, so you have the opportunity to see different ions, which again gives you a chance to provide remote sensing in it. Speeds of the plasma coming in here are about 130 kilometers coming in, which is slower than the solar wind, which is about 400 or so kilometers per second. We're talking about magnetic field that's mildly weak, but still fairly enough to produce some strong modification of the system. And we have coming into Titan about 10 to 25, 10 to 26 ions per second moving into that system.
Can you just remind us how many nanotesla the Earth's field is?
30,000 nanoteslas, so it's 1/10,000th of the terrestrial magnetic field. So even though it's small, we'll demonstrate it actually has substantial impact for how Titan and Saturn couple together.
How big is Saturn at its surface?
I've forgotten exactly that much. It's a few. I think it's almost. I think it's terrestrial-like, isn't it?
Like 20,000.
Yeah, 20,000. Thank you. And I forgot to mention that a lot of this work is done in collaboration with Darcy Snowden, who is working on Titan, Aurora, who is working on the Saturn system. I forgot to do my acknowledgements at the beginning. Saturn is also very interesting because it has another source of plasma, Enceladus, which is much closer in than Titan. It has these cracks, and it's recently believed to have plumes of gas coming off the southern hemisphere through cryovolcanism. And so this is thought to be actually one of the significant sources of plasma. So it comes out as neutrals coming out of the volcano, but is eventually ionized through some of the plasma circulating along, and this guy here is then feeding plasma into the system. And this guy is feeding a different set of ions into the system. It's feeding in primarily water group ions into the system. So if you could, again, image or pick up the UV from these ionization processes, you'd have a chance to remote sense the different planets or moons around these systems. So we have to include that source as well. So here's a sort of a cartoon. It's believed that the Enceladus volcanoes are driven by tidal heating. You have some inner core here which gets hot, causes some of the ice to melt here, breaks through the crack, and again we're talking just above freezing here, small, very low temperatures, and then comes out as H2 water vapor and ice particles moving out into it. Although I don't know whether they've actually determined why it's coming out of the South Pole yet, but still a very interesting system. Now, if you wanted to play around with some other applications of what we're going to look at, if you look at some of the extrasolar planets, you have solar-like stars here, and then what you're typically seeing is Jovian-like planets closer in to less than an AU or so. If you were to look at the ratios of the systems, for example, here's our planetary system of 60,000 kilometers, and you have your Titan of 2,575 kilometers. The ratio between the planet and the moon is about 23 to 1, and our orbital position is at about 20 Saturnian radii. So if I take a typical star, and let's call it 700 kilometers or so, that'd be our extrasolar planet then. If it's Jovian-like, call it Jovian, so 70,000 kilometers. So the ratio of your star to the planet here would be about 10 to 1. So this ratio here is very close to this ratio. And if you convert your AU into planetary solar or stellar radii, you're about 20. So in fact, you could actually say that the scaling between the Saturnian system is very much similar to the extrasolar systems, where you have these kinds of ratios and distance scales in the system. We actually have another analogue in our own system, the Jovian system, 70,000 kilometers. If we take Io, which is a smaller radius at 1,800 kilometers, but the ratio of Jupiter to Io is about 39 to 1, orbital distance about 6, much slightly closer in. Go to Ganymede, 2,630 kilometers, your ratio is 26 to 1, and your orbital parameter is 15. So there are very similar systems moving out. Ganymede, of course, is different from Titan in that it has a magnetic field to play around with. But again, you can sort of see that there's a sort of similarity between the ratio of parameters. There is an example up here that's allegedly associated with one of these extrasolar planets. They've claimed to have indicated that there's a sunspot or brightening on the stellar surface associated with the rotation of the orbital body. So even at these ratios, there is some indication that there can be feedback between the big guy and a little guy, whether that's a subsolar planet or whether it's a moon around a gas giant. So there are these analog processes that could be occurring at the extrasolar systems. And Ganymede is a more famous example of this alleged coupling. So here's Jupiter. Here's a close-up of its Aurora. And so what they see are so this is the auroral pattern going off. And you'll see these three other spots here. 1, 2, 3. This is believed to be Io's foot point, Europa, and Ganymede's foot point. So that the moons here at Jupiter are actually talking to the Jupiter and modifying this plasma environment. So again, you have some means of remote sensing here. So again, the idea is that these moons are moving through the magnetic field of Jupiter, modifying its magnetic field, moving around these field lines that map into Jupiter's high latitude regions, causing auroral emissions. And it's unclear whether Callisto has a footprint because it's right in the auroral oval, and so they've not been able to distinguish a separate Callisto signature. So in these things, this is a nice pretty picture that we're headed towards, is for Jupiter with this interaction that they can actually see here at the auroral oval with the local situ measurements. By Galileo, for example, we know that plasma is being stripped off these moons, moving up the field line and communicating energetic particles into the auroral regions to produce this kind of coupled systems between the two of them. So our job, what we started to do, was ask the question whether this same kind of plasma interaction occurs at Titan. And how does that go towards stripping, whether we can see relative signatures of what's happening at Titan versus Saturn. Now Saturn is weaker than Jupiter, and Titan is further out to play around with. Now this problem is quite a difficult problem because we've got two major scale sizes to worry about. So we have Saturn sitting at 60,000 kilometres, and we have Titan sitting at 2,500 kilometres, and your first guess is, boy, that's a teensy-weensy little object. If I were to draw it onto scale here, it'd probably be less than this laser pointer. So how can this little guy have a major effect on this big guy? And that's one of the first assumptions that most people make, and this is why we're actually investigating it, is to actually check out whether that assumption is really valid. So we've got a very big disparity in scale sizes to play around with. The Saturn system is complicated because it has plasmas leaking out from its high latitudes, which would be called the ionospheric plasma, moving out. We have water group ions coming out from Enceladus. We've got Titan making plasma, and we've got the solar wind plasma coming in here. So you've got a whole lot of different sources of plasmas coming in. The solar wind plasma conditions out there is about 0.05 particles per cubic centimetre, 400 kilometres per second solar wind speed, and about half a nanotesla coming in here from the solar wind. So again, very weak field compared to Saturn. Titan here, then it has its own set of plasma sources, the ammonia group, methane and ethane coming off it, and the incident flow coming in here from Titan has about 3 astronomical units, so it's a mixture of protons and oxygen ions coming in. Net speed is actually slower than the solar wind, carrying about 3 or so nanoteslas of magnetic field into Titan. And its incident flux is a couple of orders of magnitude down from what Saturn is seeing from the solar wind. So how do we solve this problem? So we're a bunch of modelers. We run the fluid equations, which I'm not going to show. But we're going to discuss the gridding system. So a standard thing is you would put in a gridding system with ever increasing grid spacing moving out so that we cover a very large system size. So the Saturn magnetosphere extends out a couple of hundred Saturnian radii, so it's quite large. In fact, bigger than the Sun in total number of kilometres. In both, so we've got a three-dimensional one. This is just a cut X and Y, for example. And so we have down to a quarter planetary radii resolution down around Saturn, moving out. And then what we do for Titan is we now put in an additional set of grid points around Titan to keep going down in resolution, again several times down to 100 kilometres. So we're actually able to view both the small scale and the big scale systems here. So that's what we're doing, and then we run them. Now, with such small scale sizes, it's hard to run a code unless you've got a really whopping great big code to process everything. So what we do is we use this grid system to set up an overall equilibrium. It takes Saturn several tens of hours to come into equilibrium with solar wind conditions. After that equilibrium is established, we then place in a high-resolution grid around Titan and see how that evolves around that system. Okay, so here's the parameters just again. So quarter planetary radius down to all the way down to 100 kilometre resolution, or a fraction of a Titan radius, with these species around Titan and these other species here around the inner boundary. So we put in a lump of a torus of plasma around the latitudes that Enceladus is moving around to give it its density there, and then track it as it moves out. Okay, so that's a system. So here's the look at what happens with Saturn's system when it's just where the interplanetary magnetic field is parallel to Saturn's magnetic field. All right, so here's a complicated looking figure. So here's Saturn. Now we don't go all the way into Saturn radii, so this is our inner boundary here, which is actually 2 Saturnian radii, not 1. So just for scale size, just remember this is 2 Saturn radii, not 1. We have a cut here in the equatorial plane, and this other cut here is in the noon-midnight meridian, and we're just looking at the intersection region of 25 Saturnian radius, and this little guy here is Titan. So he's just a little guy here. Color contours are of the solar wind density coming into the system. So it piles up on the stronger magnetic field to produce this round feature called the magnetopause, and then some of it's allowed to flow into the magnetic field into what's called the cusp. So here's a cusp, here's another cusp. Solar wind is coming in this direction here, so our reference frame is such that the rotational plane of Saturn is in the parallel to the z direction, so the solar wind is coming at an angle. So this cusp here is more intense than this cusp. And over here is just the density in per cubic centimetres, okay? And these guys here are the magnetic field lines that trace into the high latitude regions for Saturn, okay? And we've let this come into equilibrium, so we're looking now 38 hours after we've been blowing in, and then we've started off with 0 interplanetary magnetic field, and at about 34 or so, the change in interplanetary magnetic field has just started to arrive and soaking in, and this is when we start the run on Titan. So here's little Titan. It's got its little plasma source that you can barely see here, but as we let Titan evolve, you'll see it produce a little tail here, and with a bit of luck, you can actually see a little bit of tail here. And actually, if you go back, you'll see that the magnetic field is actually getting a little bit inflated as the parallel magnetic field arrives. So the solar wind is actually, as small as it is adding flux or magnetic flux to the entire system, and one is able to start to see those changes develop. So there's little Titan moving around, and that's in the light ions, protons. If we look, there we go, and then you can see a nice little tail developing here. Right, and now if you look at it, this tail is now getting to be quite long. This is now several Saturnian radii in length.
Robert, just to make sure I understand, you're starting off with the solar wind just about to hit it, and then you start your simulation. You let the solar wind particles come in. Is that what's changing here?
No, actually run the solar. So the solar wind has 2 components: it's the particles and the interplanetary magnetic field. We let the solar wind blow in with assumed to have 0 interplanetary magnetic field, and we let that blow in for about 40 hours to get the equilibrium, and actually 35 or so hours. And then we turn on, let the interplanetary magnetic field come into the system and see how that changes.
There's no input from Saturn or Enceladus or anything like that. It's just...
Well, we have fixed boundary conditions around here. So and this is rotating system. So as the magnetosphere changes, you can draw plasma out from the inner boundary. So you can actually pull plasma out. And so this is the extension. So we start off with a little bit of plasma around here and around the inner boundary. This is the plasma disk that forms associated with plasma coming out from our inner boundary. So we end up with a plasma disk as well.
That originated in the solar wind?
No, that originates from Saturn, either from Enceladus or from its ionosphere. So this plasma is all internal source, and most of this plasma...
So you haven't talked about, though, how you know how much is coming off of Saturn, or how do you specify that source from Saturn?
In this code, we can do that in a minute, because we have the beauty about our code is we have three ion species. We have protons, CNO group, and heavy ion group. So in the way the code is, protons are allowed to come from the solar wind or from Saturn. So here you see both of these guys and these guys. In a little while, I'm going to show you the density plots of the water group and the heavies. And they can only come from either Saturn or Titan. They can't come from the solar wind. So there we know that that's the source of that plasma.
I'm still missing how you specify whether you get the flux off of Saturn. Is it the electric field that just pulls it off?
Yeah, the electric field pulls it off.
Okay, so you just say that it's there, and,
yep.
And once I get a certain...
Yes, so what happens is you have these field lines, and we'll show a bit of movies later on, but these field lines aren't static, they're moving around. So any plasma down here that's loaded, as these field lines rotate and spin or change or convect, they'll pick up energy. So any plasma starts here will be flung down onto the outer field lines and into the disk. They're good questions. Thank you. All right. So after just 4 hours here, you can start to see the start of a disk. And in fact, going back to Woody's question here, this is just showing you the heavy ions here present here. So this is a top view now. And again, 25 to 25 RS. This one is density, and this is temperature. We've got a whole lot of hot plasma moving around. You can see that the cold stuff is here. You can actually see a little bit of spoke-like features here. But basically, you get the hot stuff just at about Titan's orbit coming in here. This feature here is known as the inner edge of the plasma sheet, where all the hot stuff is. I don't have a scale here, but this is more than a kilovolt in temperature here. And then this is stuff leaking out across the magnetopores. And again, you'll be able to see a little bit better the formation of the little tail that poor little Titan has. On this white circle here is if the material were staying in the same orbit as Titan. Okay, so we can ask the question whether it's orbiting or falling in, and you can see it step out. And you can actually see here that, in fact, it's actually falling in towards Saturn, this tail coming out. And you can see the hot plasma is now lying at this boundary between this cold plasma from Titan. So Titan then is getting a little bit grumpy because it's being whacked by all this plasma and is setting up its reaction back onto Saturn. All right. The one thing is that this magneto little tail here is very, very stable here. We see it, we've lasted 4 hours or so, and it looks like, we don't see any rapid, disastrous changes. Actually, here we go. Okay, so that's the end of that run. Oh, if you wanted to see it in just in art form here's the tail. We're applying just an isosurface of density here. These lines here are flow lines of plasma streaking around the planet, the moon, and the red ones are flow lines that are very close to the moon, and you can see the tail fall and move out. And again here, so where this tail here is close to 10 Saturnian radii long. So it's quite a long tail that is being produced by this interaction. Not only is it falling in, but it's actually sinking a little bit out of the equatorial plane. But the whole point here is it's stable in position. Its width is quite large. When it's full width, if we measure it, it's about a Saturn radius wide. So even though we start with a very small system, it gets kind of big as it moves in. Now Saturn is kind of, it's kind of a quiet day for Saturn, while the IMF is parallel to the Saturnian magnetic field. Titan then has a little bit of a rough time when we go and turn the interplanetary magnetic field anti-parallel to Saturn's magnetic field. And here's a side view, and I've exaggerated Titan a little bit so you can see what's happening a little bit. So again, this is just and this is a projection of its position. We've got it at 45 degrees, so it's a little bit, appears closer than the 20 because it's a projection effect. Okay, so here's the magnetopause cusp. This feature up here is called the magnetotail of Saturn. It's at an angle because, again, the solar wind is blowing it a little bit, so you can actually see sort of a bowl-shaped disk. Our Earth has a flat plasma sheet because it's coming straight at us on average. And what happens with the interplanetary magnetic field, as weak as it is adding or subtracting flux from the Saturnian system. So what you're going to see, I hope, is that as we start putting in that anti-parallel magnetic field, it causes the plasma to convect into the middle of the sheet here. But it's because it's a rotating system. As soon as you put more mass into the system, it becomes more influenced by rotation, and so it spins itself out. And so what you're going to see here is that this feature here will actually move down. So at the beginning of this system, poor old Titan is sort of sitting on the outside of life, but then during this kind of interaction, it gets totally immersed in a more hostile environment. So hopefully we click, and click, 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 and you can see it being now completely immersed. So if I go backwards in time, so right here, it's sitting dead square middle of the plasma sheet. If we go back to the beginning of time, it's actually sitting on the periphery. So during this time, the plasma conditions and the space environment around poor old little Titan is changing dramatically, and so it's going to have a rough time. So, and also if you look back, if you've got good eyes, you'll see once we turn the IMS southward, or anti-parallel I should say, it spins out a little bit. Once it spins out, it fluffs off some of the plasma and it shrinks back in a little bit. So there's certainly, the whole system is changing, and you can actually see some material boiling off here at near the auroral latitudes. Okay. So that's the side view. So here's the top view again. This is the CNO group, and there's little Titan. It doesn't look like much on this scale. Now what happens with anything that you're spinning, so Saturn is spinning around here, as we put more plasma into the disk, it becomes unstable, and Aurora is the one who noted this, and she's writing it up, is that you get these fingers, call them the fingers of death, okay? See them spin out, and poor little Titan is right here, and in fact it's going to get clobbered by one of these things. So if you watch it rotate around, there it goes, gets splattered by one of those spiraling arches there. And we just turned it off just as the second one was going to splat into it, so you can see it running.
It's really going with Saturn's rotation.
Going with Saturn's rotation. It's actually slightly dragging, so it's not completely co-rotational, but it is going around pretty well with it. And so you can see those things intensify and get flung out, and you can see some stuff going in and out over here as well as you go back and forth over this thing. So Titan gets splattered here, and its environment becomes different. Okay. Now, so Titan, if you look just down here, Titan is kind of pesky. So you see this arm coming around, and you'll actually see it modify, right, for example, right here, you can actually see it's cut a hole through that finger. All right, so this is this finger. It's going to come in, it's going to whack it. You can actually see on a couple of occasions here that there's an indentation in that one. So Titan is putting up a fair fight to say it doesn't want all that plasma piling up on it. And if we go closer, we can show it a little bit. So there's little Titan here on a zoom up, which we'll see. And here it comes. So it's got its tail. Here comes a big finger coming towards it. And what we see here is that if you might be able to hint that there's actually a pile-up of plasma here, slightly different color contour as it piles up. And whoops. And as you see it comes around here, you'll see that that tail gets completely pushed aside, and some of this plasma actually hooks around. So that Titan is now actually completely distorting the flow of Saturn's plasma around the system here. And then it goes away. It's like a flag post. You can see it moving away. And it tries to recover to its original position during the density minimum, but then another cloud comes through. So this is sort of a summary, is it had a nice pretty tail. Then one of the fingers come around, crush it. The finger is distorted. You can see a minimum in the density as it plows into Titan, and the tail is also completely distorted. And you can see now, instead of even being closely to co-rotational, it's completely pulled in. So in this particular case, Titan's plasma environment is not stable, that its tail can actually be totally disrupted. All right. Now this takes quite a bit of art form to get used to this plot. Okay. And we went a bit crazy with the purples here. Okay, so this is a top view of Titan. So we're just going to focus down. So now we've dropped the resolution to a couple of Saturnian radii. So this is a top view of the system that we sort of saw before. And this is a vertical view. So this is looking in the z direction. But because stuff is flowing in, on average, this direction, we've got three planes cutting it here, here, and here. So these are these three planes. Okay. And again, we're only looking at a few solar Saturnian radii. And the question that we're trying to answer by looking at this cut is not only how long is this tail, which we've already seen, but what is the up-down extent? How big is that? And so here we go into it. So, and this middle panel, of course, you can see Titan peeking out there. Darcy did this. It's quite an excellent piece of work. Here it goes. So you can see the tail punching out to here. This is the extension of that tail in there. And we've got it just, here comes one of the fingers in high resolution. So fairly uniform here. It just hasn't quite got to Titan. And you can actually see this stripe in the density here, extending several solar radii up. This is the magnetic field being hung up on Titan, not being able to twist. And so you can see it as a very permanent feature here as this guy puts up, impacts the finger. So you can see it coming in. And I'll go through it quickly. Again, here's the finger whopping into it. You can see this very distinct bite out in the density going through. And then you can see it recovering its tail and coming back. Let me go back. So you can see this thing is there. It's certainly moving around but certainly a present feature for a very, very long time. The reason that's happening is the magnetic field is piling up on this guy, and that means you have a chance of accelerating particles, making aurora, modifying the entire Jovian system, in fact. And you can also see it in temperature. So this is the ion temperature, again, kilovolts is up here. So we've got a whole lot of hot plasma. Titan is nice and cold. Stuff is coming through, and you can again see Titan making striations here in the temperature profile, and it's still quite persistent in here. It's remembering the old plasma. Here's the cold bit. Plasma streaks up here. And there we go. So for us, who's doing space physics, this is kind of an important effect, because at this kind of scale size, this scale size is almost closely equivalent to the entire width of the plasma sheet of Saturn. So stuff is trying to come in, trying to make aurora. It appears that Titan may in fact be setting up the point when it's in the tail about where the inner plasma sheet should be, which would then affect where the aurora might be occurring. And so this is a fairly strong prediction that's being made here about its influence when it's in the tail, because it's certainly modifying it. And you can see the nice vertical stripes here. So it's having a big effect. So summary, let me just say that we've played around here with Saturn's plasma environment. We see that the solar wind and interplanetary magnetic field have influences on the system from the interplanetary magnetic field. It couples to the planetary magnetic field, and with its fast rotation sets up our magnetosphere, which is then quite variable, and this means that we have a variable plasma environment at Titan. This leads to induced a magnetosphere around Titan, but it certainly leads to enhanced stripping of Titan's atmosphere. It leads to specific ions that we can actually track out from Titan, so that you can see, for example, in our case, difference between the nitrogen that would be coming out from Titan versus the O+ coming out from Enceladus. And so these definitely mixing of plasmas. We see that we have an extended tail out to at least tens of Saturnian radii, but it's certainly subject to disruption due to changes in the solar wind conditions. Conversely, Saturn is able to then, since it's such a large tail, is actually modifying Saturn's plasma system. And so there may in fact be really strong two-way coupling, which we're still continuing to research. I'll leave it there. Thank you.
Question? I've got wood.
Well, you bring up a very interesting thing here at the very end, of course, the stripping of the atmosphere and so forth.
Right.
So you haven't put in any of that coupling yet. Is that part of what you plan to do?
There are a couple systems now. We're still running the numbers because it's highly variable, and so we didn't realize it was going to be as variable, but we see nearly an order of magnitude change in the outflow of the Titan ions during some of these events. So it's oscillating very significantly, and we need to plot out exactly what that change in flux rate is, but it's orders of magnitude changes.
Yeah, but that'd be extremely interesting to see what the time averaged is, as well as the variability. And
yep, we haven't gotten that far yet.
And then obviously the atmosphere is there; it hasn't been stripped, so that implies you've got to have the input.
Yeah, I still think this is not a real fast stripping mechanism for Titan. I think we're losing. It's just like a standard type of system. I think that's 10 to the 25. I think that works out to be, let's see, Io is a ton a second. I think this is only a hundredth of a ton per second or something.
Can you relate that to atmospheres per billion years?
I think the answer is, I think the standard answer for most of the moon system is of order of a few meters per billion years, is what we typically strip at. of ice. If I condensed it into ice, I could solid, yeah. And you guys would have to convert solids to gas. Figure out how much that is.
Go ahead.
This is a little bit tangential, but going back to Enceladus.
Yes.
You mentioned water ions being injected, but you also mentioned ice particles being injected.
Right.
What is the nature or fate of that particulate? Does anybody have an idea?
Okay, Carol can do it. She's working on that.
Actually, the particulate ice in the dust is what they believe makes up the whole E-ring. And the E-ring is superposed on Enceladus' orbital location. It's looking more and more like the coincidence is pretty impossible. Like Enceladus is feeding the source for the dust and the water is for the E-ring, which is the most diffuse of the rings. It's not one of those flat, disky ones. It's a big, diffuse Gaussian.
How does the results of your computer modeling compare to what Cassini has actually measured?
We're actually doing pretty good. I think we're the first to actually, Ryan's supposed to be writing this up, first to identify the source mechanism for the fingers. They were observed by Cassini and were able to start producing that. Darcy has worked up Titan's close in to Titan and able to reproduce the magnetic field signatures there. And then this modelling here is then providing a link between those two sets of observations, which you can't really do from the very few Cassini observations. So this is providing an important link. Just recently a paper was published by people at Iowa indicating that Titan is in fact modifying the radio emissions from Saturn. They have, so Earth and Jupiter and Saturn are actually bright broadcasters in the radio, and in fact can be brighter than the sun in the radio. At Jupiter, it's well known that a lot of those radio emissions are modified by the moons. The first result that Titan is modifying the emissions at Saturn has only just been published, and this work here is providing a means to explain that coupling, which hasn't been developed either previously.
If I could just inject brighter than the sun at those low frequencies.
At those low frequencies,
Not
yes.
total energy.
I didn't say that. I said at those frequencies. At the radio, yeah. We get to cheat.
Anything from outside?
No question from either.
I've got one. If Carl Sagan is right, or was right, and there's life on Titan, how is it being affected by the magnetosphere and the plasma environment around the planet as you've modelled it?
Right now, most of the stuff is low energy. Saturn's magnetic field is too weak to really get a good radiation built up at Titan. So right now, those little bugs be nice and happy. No effect. We're just boiling off some of the material at the top. The question is, what happens when you're an extrasolar planet if you're going hunting for those guys? Now you're in a much hostile plasma environment. Presumably the may or may not have stronger magnetic field. You may have a lot more energetic particles, and then the little bugs out there may have some more interesting life.
We do have a question from outside.
Ben Tian has a question.
Oh yeah, I just wonder, what if you put an intrinsic magnetic field on Titan, and how that will affect the mass loss rate? Will that reduce it significantly? This is a hypothetical question.
Oh, that's a real good question. We've not done that for Titan, but we've done a little bit of exploratory work for Ganymede, which does have an intrinsic magnetic field. There, the loss rates are about the same, but what happens is the energy is concentrated into the poles. And if you look at Ganymede, for example, the ice looks cleaner on the poles, and it's dirty in the middle, which is protected. So you get faster stripping at the poles. So you concentrate your energy into those systems. in a system which also has an intrinsic magnetic field, you get conversion of some of the magnetic energy into particle acceleration by a process called magnetic reconnection. So you may have a more energetic particle environment than we have for this induced magnetosphere at Titan.
Thank you.
I've got a follow-up question. If you were to project either a few billion years into the future or a few billion years into the past from your 40-hour simulation, can you speculate about the possible history of life on Titan as a result of its magnetospheric and plasma environment? Sorry. I apologise for that question.
Why aren't you asking me about life on the Galilean moons rather than Titan? Titan is kind of cold, isn't it? So
yeah, but let's say there's weird life out there that can cope with it. I mean, let's say there's you know a domain Barosia out there that has methane, has ammonia as its solvent, and lives by converting ethane to methane or something.
Okay, I'm not going to answer that one because you're right. Thank you.
Questions? Well, thank you very much, Robert. Before we leave, I should mention that Robert is also newly installed director of the space grant here. So if anyone wants either some space or a grant, everybody at universities wants. See Robert about.
And I would put in that we have instigated some graduate student support. So if you're out of graduate student support, even though Astrobiology has more funds than we do,
not anymore.
We have instigated some graduate student support as well as undergraduate.
Okay, so I'd like you to join me in thanking Robert.